When we are testing for a linear relationship in linear regression, we want to come up with a format so that we can check to see if there's evidence or a significant, in a statistical manner, linear relationship between our x and y variables. We begin by defining our hypotheses. Under the null hypothesis, we would say x and y are not correlated or linearly related. We could also say the correlation is 0 for the population data. Under the alternative hypothesis, we say that x and y are correlated or they are linearly related. In this case, we're saying the correlation coefficient for the population is not equal to 0. Next, we would write our decision rule, which will say to reject the null hypothesis if the p-value is less than or equal to some given level of significance. Then we would need a test statistic. In this case, we're going to use the sample correlation coefficient that we get from software, or the value of R. So let's perform this test, and then we'll go through the other steps which follow for our wolf data. First, the null hypothesis can be stated as tail lengths and weights of wolves are not correlated. Or we could say the correlation coefficient for the population equals 0. Under the alternative, we can state tail lengths and weights of wolves are correlated, or the correlation is not equal to 0. The decision rule would be to reject the null hypothesis if the p-value is less than or equal, and we will use a standard 0.05 significance level. Next, we run the analysis using the StatCrunch software, and the next few slides will show output, and then we'll talk about the parts we actually need. First, StatCrunch will produce the following text. It will tell you a simple linear regression was run where the dependent variable, or the y variable, the response, was weight, and the independent variable, or the predictor variable, was tail length. Weight equal 48.4 plus 2.5 times tail length is the equation of what we call the line of best fit. The sample size was 10. There were 10 wolves in the study who had their weights and tail lengths measured. The correlation coefficient R is calculated as 0.69260048, and a lot of times we will round this off just to a few digits. The R square value literally is R raised to the second power, and that turns out to be 0.47969 and then some other digits. And we'll talk about how we interpret that in a later video. And the estimate of the error standard deviation is used in estimation and prediction, but we will talk about very little of that. We'll just sort of give a brief overview of estimation and what you're estimating, and then not really go into a lot of detail. But this is a number that is used in some background calculations. So the 3 lines of output we're going to focus on are in bold, and for now we're just focusing on the correlation value being that 0.6926 number. Now another table we need is given below, and it has parameter estimates. In this case, notice that the slope row, so it's the second row in this table, okay, is going to give us the p-value under that last column, and it's 0.0264. That gives us our p-value we use in the hypothesis test. Another way that you can do testing in simple linear regression is by testing really that 2.5 value, and that involves a t-test. So if you look at other books or you look at online resources, you may see a t-score used in this hypothesis test, and that would be that 2.72 number. The p-value, 0.0264, is the same regardless of which of the methods you use. Now another table that can be produced in the output gives predicted values. Okay, so it gives X values like 16, 24, or 30 inches for tail length, and then it gives you some predicted Y values and some intervals, and we'll talk about this table later. Let's complete the test for the linear relationship. The test statistic is the value of the sample correlation coefficient R, and we'll write that as 0.6926. The p-value we found in that table as 0.0264. Now we need to make our decision. Well, the decision will be made to reject the null hypothesis. That is because 0.0264 is less than 0.05. Then we could write our summary as at the 0.05 level of significance, there is sufficient evidence to conclude that tail lengths and weights among wolves not just are correlated, but we can actually tell they're positively correlated. And we can tell that it's a positive correlation because the value of R is positive, or if we go back and look at our scatter plot, we saw an increasing trend in the data. If X and Y are found to be correlated, we will fit a straight line that best describes the relationship in the sample pairs of data and use it to draw inferences. This involves a line of the form y equals mx plus b from algebra. Now the value of b, which will be the number that sits alone in the equation, whether it's written first or second, and you can interchange the two components, but the number that's by itself is the estimated y-intercept. Now this would be where the graph of the line crosses the y-axis on an xy plane. It's the expected or typical or average value you expect for y when x equals 0. The value of m, which is the number multiplied by the predictor variable in the equation, is the estimated slope. Now this measures the change in the response variable y for each unit increase or increase of 1 in the x variable or the predictor variable. To find this best fit line, we use a method called least squares. Least squares means that if you determine how far from the line each observed y value is. So if you fit a line and you say how different is the y value of the line and the actual y value I got in the sample for that x value, and then I square that, and then I add up all these squared terms, and then I make that as small as possible. I minimize that using mathematics. Basically, that's what you're doing. You're finding the line that minimizes how far away the squared distances between what you actually observed and what the line says you should observe would be for the data. Now we're going to use StatCrunch to find the line, and we're going to focus more on interpreting the slope and then sometimes the y-intercept in a given scenario. Now the table that we're going to need to find the line is the parameter estimates table. And again, there's a t-value in this table if you wanted to do testing using a t-score instead of the correlation coefficient. Okay, but we're not going to do that. Now the slope estimate is 2.5. Notice it's on the row that says slope under the column that says the estimate. The y-intercept estimate is 48.4. It's under the row for intercept and column for estimate. So we would write the equation in general algebra as y equals 2.5 times x plus 48.4. Or in our scenario, we would be saying weight equals 2.5 times the tail length plus 48.4. One warning, if either of the values, the slope or the intercept, is negative, be sure you account for that in your model by putting that sign in when you write your equation. For our example, the line of best fit was weight equal 48.4 plus 2.5 times tail length. So notice now the number by itself is first and the number multiplied by the predictor variable is second, and this is the way a lot of statistical software will write out models, because when you do advanced modeling you can add more variables easily onto the end. But for us, the y-intercept is that 48.4 number. Now mathematically, this means that if the tail length, the x variable, is 0 inches, then the weight, the response variable, or the y variable, we would expect to be about 48.4 pounds. This is really inappropriate for a couple of reasons. Number one, the tail length is not going to be 0. Okay, a lot of times when you think about the predictor value being 0, that doesn't make sense in the real world. Another reason is that our model was created using tail lengths that went from about 10 to 28 inches or so, and 0 is not in that range of values. Now, interpreting the slope. For our example, again, the line of best fit was weight equal 48.4 plus 2.5 times tail length. The slope is the number multiplied by the predictor variable. So the slope is that positive 2.5. So what this means is for every increase of 1 inch in tail length, the weight of a wolf will, since it's positive 2.5, it will increase by about 2.5 pounds on average. Now we know it increases because the slope is positive. Visually, what does the slope tell us? So let's go back and review what this would look like for a certain case. Suppose I start with a tail that is 16 inches. Okay, so that would be just to the right of the 15 where this line is located in our graph. Now if I move up 1 inch to 17 inches, okay, I've gone a distance, or I've increased by 1 inch at this point. So that distance between those vertical lines is 1 inch. How does that change the weight of a wolf? Okay, so what is the change in the y value? Well, that's this distance, and that leads to an increase of 2.5 pounds. So as I go to the right 1 inch, I go up 2.5 pounds. In general, keep in mind you should never interpret values outside of the range used to build the model. That is going to be very important as we get into estimation to make sure that you don't violate good methodology. Many examples lead to models where it really is not appropriate to interpret the y-intercept, so sometimes you will not be asked to interpret the y-intercept. The slope we will always interpret. Now sometimes, due just to the units of measurement for the predictor variable, the x variable, I may use something other than just increasing x by 1 unit in an example. But a lot of exercises can be done by saying if x increases by 1 unit, this is what happens to y. If you were looking, for example, at weights of diamond rings, those are measured in carats, and a lot of times you don't increase by a full carat at a time. So you may increase by 1/10 of a carat or 1/4 of a carat and look at the resulting change in price of diamond jewelry. If you were looking at gas mileage for cars and basing it on the weight carried in the vehicle, you don't want to increase the weight just by 1 pound because that's such a small difference, but you may increase it by, say, 120 pounds or 150 pounds, which might be like carrying another person in the car. So having an additional person in the car, how would that impact gas mileage? So in that case, we're again not increasing by 1 unit, we're increasing by 120 or 150 pounds. How does that affect the miles per gallon? But the slope will always be interpreted. So keep in mind, this is the way you do hypothesis testing and interpret the y-intercept and slope from the line of best fit.